Hi Nine, I'm going to attempt to record a video for you today so that I can go through the homework that you handed in last week and hopefully, just as I might at the start of a lesson, go through that, help you through any misconceptions that you might have had. Now I know that I've still got hold of those, but me going through it will hopefully help you to understand, and I'll keep hold of them and give them back to you when I next see you. So the first thing that I'm going to do is go through the opposites attract sheet and hopefully improve your understanding. So the first question asked, magnesium is a metal which burns readily in oxygen, forms magnesium oxide with formula MgO, and asks you for the ratio of those atoms. Clearly that's just 1:1 because magnesium oxide told you the formula was MgO. The real questions that we need to focus on are the ones which involved the dot and cross diagrams, and most of you were fine when you were drawing out the diagrams of the atoms. So a magnesium atom has 3 shells, and that holds, the first shell, as you know, holds 2, second shell also full at 8, and then the third shell for magnesium holds again just 2 because of course it is in group 2. Oxygen, which was the other element involved, also has a first shell of 2, and we'll use dots this time, and the second shell has just 6. So you can see that neither of those atoms have complete shells. Now in question 3 it asked you to explain how magnesium oxide was formed to achieve full outer shells, and you had to do this by a description. So that was the important thing there, was to remember to say how many electrons were moving, whether they were lost or gained, and the fact that they were moving from or to the outer shell. So magnesium, of course, loses these outer 2 electrons, so loses 2 electrons from the outer shell. Those are transferred to oxygen's outer shell, and so oxygen gains 2 electrons into its outer shell, and that then would become full. Because then the magnesium's outer shell would then become the next one in, because this one would have gone, you've now got a full outer shell which holds 8, and this oxygen one would have picked up 2 more. Now when we pick up 2 more, those are going to be shown as crosses. Now I'm just going to get rid of this outer shell for magnesium, because if you were drawing this separately you wouldn't want that to be shown. So, at the moment, I've got what some of you would draw for the product of magnesium oxide, but there is an important thing missing, and that is the charge. Because if you draw that as the electron diagram, that is identical to the noble gas neon, which also has a total of 10 electrons, like this now has. And of course this is not neon. You can have a think about why that's not neon. If you pause the video, have a think, what is there to show you that that's not neon? Why is a magnesium ion different to neon? When you think you've got the answer, press play. So the reason that this is not the same as neon is because of course neon would have a different number of protons in its nucleus, and also because of that magnesium now has 2 less electrons compared to its protons. And if it has 2 less electrons, that means that it has 2 more protons than electrons, and therefore overall a 2 plus charge. So 2 more protons, which are positive, than electrons, negative, giving a 2 plus charge. The oxygen ion, which remember becomes what we call an oxide ion, has gained 2 electrons, and so that now has 2 electrons more than it has protons, and electrons are negative. So the charges on those ions are 2 minus. So we have our magnesium ion, 2 plus, and our oxide ion, 2 minus. And you should always show those ions. So even if most of the time they will be asked for, and you will be given hints that you need to include the charge, but you should remember that ions are charged particles brought about by an uneven number of protons and electrons. So that was what you had to answer. The specific charges in question 5 relate to those charges there. You were asked in question 6 what type of bond that was. Of course, we've been studying ionic bonding, and so the bond is an ionic bond. Now I'm going to go through number 7, and that asked you to do the dot and cross diagrams to show the structure of the way that the bonding is in lithium oxide, and it told you that lithium oxide was Li2O. I'm just going to clean the board, so again I can draw that there for you. Now, if you remember, when I went through this in the lesson, in your books, we showed the thought process, and some of you, well, we were drawing arrows to show the movement of arrows, but I did make quite clear in your notes that the arrows are not required by the examiner. What they are interested in is they are interested in the final ion structures with the outer shells now complete and the charges on those ions. So if you know that the formula is Li2O, straight away that tells you that you must have to draw 2 lithium ions and 1 oxide ion. Now a lithium atom would have 3 electrons, 1 electron which would have been in the outer shell, but of course that 1 electron is the electron that it would lose, and so a lithium ion, having lost its 1 outer shell electron because it's in group 1, would have a positive charge. The lithium ion is now content, it has the full outer shell. If you think about what it's going to attach to is an oxide or an oxygen atom first of all, which has the 2. And then remember it has 6. Now if this lithium, when it was an atom, lost an electron, that would put 1 in the outer shell. But remember that that oxygen ion, or the oxide ion as it wants to become, wants to be full. So it would need another one. So remember that is why we need another lithium ion, which has given its outer electron from the atom into our oxide ion. So now that's got 2 electrons more than it has protons, and so the charge is 2 minus. So the 2 positives are cancelling out with the 2 negatives, and so the formula Li2O has no overall charge. The final one that you're asked to draw, which I'll just go through. Okay, so the final one you were asked to draw was potassium chloride. Now potassium is again in group 1, but it's much further down the periodic table, and it has therefore more shells, so it has 2, then 8, and then it's got another full shell of 8 before our final shell for the potassium atom would have 1. But remember, that's the one that we're going to lose. So what the examiner wants to see is the ions. So having lost that outer shell electron, remember we need to show that it's no longer going to be, it's not going to look like the noble gas with that electron structure because it is charged, and it's going to be single positive charge. We don't need to show the one, but just plus, and that's because it's lost one electron and it ends up with one more proton than it has electrons. The chlorine, again, that is a slightly larger atom, so chlorine. Again, I'm going to need to show 3 shells, which I can just about fit on here. So 2, 8, so I'm showing dots this time. So I've got dots and crosses, and then the outer shell of chlorine would have had 7. And that is the one that picks up, that just needs one more, so the one electron that potassium loses from its outer shell goes into the outer shell of our chlorine atom, and that will mean that overall our chlorine atom has become a chloride ion with a single negative charge and just about squeezing our bracket to make it complete. So that is a potassium ion. And that, remember, the name is a chloride ion. So the ending of the name changes. And the formula is KCl because you've got 1 potassium and 1 chlorine. One thing that you must ensure you do, so I don't want to see any of the arrows for what's happening. If you have to draw that, that's fine, but keep going until you've got this. And what we don't want to do is see a combination of the two. So some of you were trying to sort of draw the outer shell and you're having the electron showing it transferring across, and you were trying to draw the electron, you know, twice in the outer shell, and you were sort of putting it there and then giving the charges. And some of that then is right because you've got the right electrons and the right charge there, but of course this one over here, some of you didn't have the charge there, which is supposed to be positive, and also that electron shouldn't be there anymore, and I don't want to see this arrow. Okay, so, and ideally the final thing is that unless you're told, remember, you should be showing all of your shells. Sometimes we just focus on the outer shell because it makes it a little bit quicker to demonstrate on the board or in your book to practice more examples. Okay, so what I'd like you to do now is pause the video, and if you complete the starter slide into your books from the PowerPoint that I've attached. When you finish that, the answers are on slide 2, and the next task that you can do is to move on through the multiple choice questions just to test your knowledge, which are on slides 4 through to 15. Once you've done that, then turn back on the video and watch this final bit where I'm going to explain about the structure of sodium chloride so that you understand what that's all about. So, hopefully you've now done your starter, got that in your books, and you've checked through the multiple choice questions to make sure you've really understood what's going on. So now what I want to talk to you about is this structure. So far we've been talking about the bonding. So that is how the ions are joined together and the type of bonding. What we're now looking at is the structure. And this is an ionic structure, or part of an ionic structure. This is part of a sodium chloride structure. Remember, we mustn't use the word molecule because sodium's got a metal, and this is not a molecule. So you don't have one sodium and one chlorine atom in a little group. You can see this is part of a much bigger thing. And the structure, the name that we give this structure for any ionic bonded substance is a giant structure. So what you can see here is you've got the green spheres and the silver spheres. The green are chloride ions and the silver are sodium ions. And so what we've got is a giant lattice constructed of alternating sodium and chloride ions. Now if you look at one face, you can see that they are alternating. So every other one is the different colour. And that will happen on all faces as well. So as you progress through the three-dimensional structure, they're alternating throughout. The reason that the formula is NaCl is for every one sodium ion, you will have one chloride ion. So overall, the ratio is 1 to 1. But in reality, you've actually got a whole load joined into a lattice structure. So one sodium ion, if you sort of look into the structure into the middle, one sodium ion is actually surrounded by 6 chloride ions. Now, what is holding this together? Now, some of you say, well, there's these little sticks here. That's not, of course, what I mean. Some of you will say, well, it's being held together by ionic bonds, which of course is right, but the question is, what is an ionic bond? So an ionic bond, have a think, what do you think it is that's holding these sodium Na plus ions together in this structure with the chloride Cl minus ions? Pause the video if you need to and have a think. So the answer is an ionic bond is the attraction between positive and negative ions. So that is what's holding it together, the attraction of the chloride ion, the Cl minus, for the positive sodium ion. And we give that a scientific name. We call that an electrostatic attraction, the attraction of something that's positive for the attraction of something that's negative. So that is what's holding it together, that electrostatic attraction. Now, what you need to do now is you need to go back to Insight, where I will have told you exactly what else you need to do to finish off the lesson. I'll also probably attach a few other video clips that you can watch to help you understand it all. Thank you for listening.